Hello everyone, welcome to iCANX Talks. Yeah, today I'm a moderator. It's warmer greetings from Beijing, Alice Jiang here. And I'm so proud that to introduce today's talk, well, our big panels. We have Xiaoning to deliver a talk. We have big panels for the discussions. So let me first introduce Professor Xiaoning. Professor Xiaoning Jiang was a distinguished professor at the North Carolina State University, and he also was my mentor. I can say that because a long time ago, she be, in the same lab, but not overlap that time. But Xiaoning was always, yeah, our big model. Yeah, so many, of us was talking about Xiaoning's story. So actually, Xiaoning got a PhD in Tsinghua University, and after that, he go to US. And after a few years, he spent some time in the industry, and then he go back to the academic, go to North Carolina State University, and he published many papers, and he also published many books. Yeah, and at least the six books, two books and six book chapters, and he issued 11 U.S. patents. And he was, attending over, hundred, conference as a super, invited speakers. And Professor Jiang also served as a vice president for the technical activity IEEE Nanotechnology Council, and he was co-editor in chief of the IEEE Nanotechnology magazines, and his IEEE NTC, distinguished lectures, also as ASME fellows, SPIE fellows, and IEEE fellows. So Xiaoning, proud of you. Stage is yours, please.
Hey, thank you. Thank you, Alice. Let me
Let me stop. Okay. Yeah.
Right.
Hey, please.
Yeah. Okay. You can see my screen, right?
Yes, I see. Come to the full screen, please. Yes. Oh, double.
Oh, this is the same. Sometimes give me I need to move this around.
Yeah.
I need to share that again, right?
Okay. Yes, you can. Oh, same. Yeah, you can. Yeah, create and reshare.
Where's that thing? It's gone. Okay, it's here. Switch.
Beautiful slides.
Yeah, it's here. Okay, got it.
Yes. Good.
And then I need to move this in the top or back. All right. Okay, thank you, Professor Jiang. Hello everyone. I also really appreciate this great opportunity. I know iCANX, has so many great. I admire the speakers. I admire all the time, and also I see the coming speakers. Again, they are all the leaders in all the fields, and really, I'm really feel humbled to give this presentation here to share with the audience of iCANX about our recent research toward the precision biomedical ultrasound. Also, before I get started, thank the panelists. Here I have Dr. Jiang from Beihang University, Dr. Howell Kim from Yinghai University. I have Dr. Mengdi Han and Dr. Jiang from Peking University. Thank you for joining me today. Now, let me get started. All right. Okay. Let me try to have the laser point. Before I get started, looks like I have a bar here. Okay. The NC State University is located in the Research Triangle Park. If you know, familiar with the U.S. map, we're in the East Coast. Right here is the Atlantic Ocean, right? And the north us will be Virginia. You get to D.C., New York City, Philadelphia, Boston in the north. Get south, you get Florida, and go to the west, you have Texas, California in the west, right? If you zoom in, North Carolina, map is here, as you can see. I zoom in further, I can see this triangle really means the Research Triangle Park. We have Duke University, UNC Chapel Hill, and NC State, with 3 major universities were located within this triangle with the longest side shorter than 20 miles. So that makes us really convenient for us to, communicate among those 3 universities, collaborating. And also not just research here, Research Triangle Park, these 3 universities are also really good. They're very well known with their sports. You probably know March, usually we say March Madness, right? So March is the time the American, the North, what we call NCAA, as the university basketball, league tournament. And all 3 universities and already in the 16th, but unfortunately UNC lost last night. Duke and NC State, we too still will fighting for we call it Elite 8. So now they're already in the Sweet 16. We're trying to get the Elite 8. This is not easy, right? But also not sports, not just research. North Carolina is a beautiful state. You can go to the west side, you will see the Great Smoky Mountains, beautiful all the season. You have, spring, summer, fall, winter, all different. If you go to the east, Atlantic Ocean, you see the very skinny, like a curve, very beautiful curve here, right? You extend it to Atlantic Ocean. That's called Outer Banks. We have more than 100 miles of those really long, skinny islands over there. Again, very beautiful for tourists. So if you have chance, you are really welcome to visit us at NC State. Spend some time here. All right, now let me take a look at this. The work I'm going to report first. I know the audience probably is with different background. So the first slide I have here is I want to show a little bit about acoustic waves. There's something here is annoying. Okay. All right. Acoustic waves is nothing but this we call it also called straight waves. It's kind of wave in both spatial and temporal, right? At any given time, you have acoustic. This is the typical acoustic pressure change over the distance or location, right? If you get at any given location or position, the acoustic energy or pressure will change over time. So that's what we call, they have the spatial and temporal dependence, right? And acoustic waves, because of this waves, you have a wavelengths or period, right? That corresponding to the frequency. Because of the different frequencies, acoustic waves, can be divided into, we said below 20 kilohertz, that's the audible frequency range, right? And above 20 kilohertz, the big range we call the ultrasound. There are some high frequency ultrasound that's even, above 20 megahertz. And most of the ultrasound industry, domestic or underwater ultrasound actually in low side between 20 kilohertz to a few megahertz here. Medical imaging, medical ultrasound, most of that, around 2 megahertz to 20 megahertz, or a few above 20 megahertz, right? We utilize this as a tool, diagnostic tool, and a therapeutic tool, but not just us, right? We all know there are some animals take advantage of this ultrasound as well. This is a chart created by Mengyue, one of my current PhD students, to show biomedical ultrasound, which is what we are focusing on today. There are numerous of these biomedical ultrasound applications nowadays. Since over about 70, 80 years in the past, we have diagnostic ultrasound can go to monitor neural activity, blood pressure. You have imaging of different organs, and even can go inside interventional intravascular imaging, right? For the therapeutic side, the recent newcomer is neuromodulation using ultrasound. We have blood clot removal, thrombolysis, drug delivery, tissue ablation, histotripsy, so on and so forth. And with what we are talking about today about precision biomedical ultrasound, the precision biomedical, what I meant, it really is you look at in the temporal, spatial, or functional wise, they can, get to the next level in terms of the imaging resolution, or you can measure something more accurate, or you can hit the target therapy more accurately, or this is the imaging guided therapy, or in the time-wise, we just not only can get high, frame rate kind of imaging, but also we can offer a continuous monitoring using ultrasound. And also precision biomedical ultrasound also means that we should look at personalized ultrasound, not just ultrasound equipment fit for all, right? We know now, for the children's, we should use the different frequency ultrasound compared with adults. And we also should know with different people who have different weight or some other characters, right? We should also consider the personalized ultrasound. So those are the pretty broad range of precision biomedical ultrasound. We're here, this slide, we want to look at the challenges in ultrasound imaging therapy here, right? And really challenging, look at the imaging. I put down one microscope, one telescope, but really people want to have one tool. You can look as far as into the space like a telescope does. And in resolution side, you also want to look at the cellular level kind of activity, but there's no such tool, in the optical scope, right? Similarly, in ultrasound, we want to give an example. If you want to see the OBGYN to see the fetal image, but at the same time, you want to see how the blood vessel, blood flow, within a certain, let's say, in the brain area of the fetal. That's also very challenging nowadays, right? So there's something contradictory with each other. That's a challenge. As a researcher, or scientist, or engineer, we would love to see challenges like this. Okay, if you come to the ultrasound therapy or drug delivery, we really targeted ultrasound. You want to target that acoustic energy to the region so that either drug delivery or treatment can be focused, right? And the good thing for ultrasound therapy, one thing is non-invasive. It's similar like I borrowed one photo from Baidu. It's called 隔山打牛. You know what Chinese audience, you should know what I meant, right? We know that there's one Kung Fu or Qigong kind of master. He can hit the cows on the other side of the mountain without even getting close to the cows. We don't know if that happened or not, but that means something. It's non-invasive, right? And then they can hit something target very accurately. Similarly, in the therapeutic ultrasound, we want to do that. But we all know with the ongoing clinical therapeutic ultrasound, they can do something very similar to the 隔山打牛, but there are some challenges over there. We still want to improve how we target better and deliver the drug in a more precise way. So what I will report today is more about progress on precision biomedical ultrasound, trying to solve some of the ultrasound imaging and the therapy and drug delivery challenges by looking at interventional and implanted ultrasound and wearable ultrasound for continuous monitoring. This is the chart about precision biomedical ultrasound. It's pretty broad. It go with the extracorporeal. That's wearable ultrasound for continuous monitoring. Beautiful works from UC San Diego, Dr. Xu's lab, and MIT, Dr. Xiang Zhao's lab. Audience in this platform probably have heard from them before. This is ongoing, definitely. In recent years, it's a big thing in ultrasound field. And our lab also, we look at this small, minimally invasive ultrasound. This is the vortex transducer BOA presented last year with a small catheter, yet we can generate the acoustic vortex. And some other labs also work impressive work. Recent work is about implantable ultrasound. Ultrasound not just non-invasive is one of the unique characteristics, but implantable or minimum invasive can also play a big role in precision biomedical ultrasound. Here are the outline of this talk. I will briefly look at the background and look at the recent progress in our lab. I'll look at intravascular ultrasound, interventional ultrasound imaging, look at intravascular sonothrombolysis, and ultrasound trigger drug delivery, and the wearable ultrasound. It's pretty broad, but I really hope to report to you what we recently achieved. First, let's look at intravascular ultrasound imaging. The intravascular ultrasound imaging was born in late 1980s. What that background is for the newborn baby or people in the healthy age, you see the coronary artery is beautiful. The lumen is fully open, right? So it's round and fully open. There's nothing narrow. But unfortunately, with most of people who are aging, we see this kind of plaque build up within the coronary artery. That plaque gradually, build up. If you enjoy the food, especially certain type of food more, this build up speed probably will be faster. And at a certain age, symptoms will start develop, right? And then people went to the hospital. Doing the first thing we'll do the angiography using X-ray to look at whether or not the key coronary arteries whether they're still fully open. Most likely they have narrow, but angiography is a projection, 2D image in the longitudinal direction. It's hard to see the cross section, right? That's how the intravascular ultrasound was invented. Yeah, as you can see here, those are the two intravascular ultrasound images to show the cross-section B mode image of this coronary arteries. It's lumen, how much open, how much blocked can be clearly seen. So that's really, the revolution in that age. Currently, there are two types of commercial or clinically used intravascular ultrasound, or called IVUS. One with a single element with a high-speed rotation. This is a 3 French catheter or 1 millimeter in diameter. So this is a very small, very, very precision kind of ultrasound device. And the other one, they have a 6-4 element array, circular array. You don't need to rotate that, but you can still obtain this kind of 360-degree B mode image of a coronary artery, right? So as you can see here, through the years, people really still want to see how they can enhance the spatial resolution, how they can enhance the contrast, how they can improve the vulnerable plaque identification, right? So all those are the challenges. And one of the challenges we addressed early years was, most of the current IVUS transducers, they use this we call plate mode with a single piezo plate. That's a thickness mode coupling. We know this is not as great. The coupling coefficient KT is not, comparable with the bar model, this K33, right? We know the square of this coupling coefficient suggested the electromechanical energy coupling efficiency. So that's why in the 1980s, discovery from Penn State University find out that the 1,3 composite that can take advantage of the coupling coefficient K33 and still have a relatively kind of easy or stable plate type of configuration, right? So as you can see here, each the colored bar or post, that's the piezo material. The white curves, those are the epoxy passive material. So this 1,3 composite is a big thing, in the conventional ultrasound for broadband ultrasound transducers. But the downside for IVUS back to at the beginning of the 2000s, it's hard because if you form the 1,3 composite curve or the spacing between the two neighboring piezo pillar, that's very challenging, because if you go for IVUS, you want to get high frequency, high resolution, and then this curve needs to be really small. How small it is, it can go, a couple of microns. Definitely the Dyson saw, the conventional manufacturing method cannot do that. So we came up with this micro machining technique. As Professor Jiang mentioned, my training, early days, my training was about MEMS at Tsinghua University. So what we did similarly, we prepared this piezo wafer, polish them, and bring that into the clean room, do the lithography, do the hard mask, electroplating, and then we do the plasma etching. With that plasma etching, as you can see the SM picture here, this piezo pillar can the side length of this is about 15, 16 micron. The curve between them is 5 to 6 micron. Then we form them in the 1,3 composite, as you can see there. And with this success, we build that into a 40 megahertz single element transducer. This was collaborated with Boston Scientific. As you can see, the pulse echo test. Our bandwidth is similar. The center frequency is similar, but bandwidth, we are the winner. And also the sensitivity, we're also the winner. For those of you doing the device, if you win both bandwidth and the sensitivity, that's not an easy task, right? But because of this 1-3 micro machine, 1-3 composite or PC, piezo composite micro machine ultrasound transducer, we were able to achieve that. And then we did this animal test with Boston Scientific. And as you can see here, the left side here is the conventional commercial 40 megahertz image. And you can see with our 50 megahertz PC mod, the resolution wise, I hope you agree with me, we have better resolution. This is a swine model imaging, but this pig was pretty healthy. We were able to see the intima layer clearly. There was no plaque was built. I also want to take this opportunity to thank my mentor, Dr. Jiang Yuan Jianren 先生. He passed away in January. As we all in the ultrasound field all know him. He's truly a pioneer in high frequency ultrasound and ultrasound transducer arrays. And he has been promoting younger generation in this ultrasound field tremendously. I really appreciate all the support from Dr. Yuan. We're also going to organize a memorial session for Dr. Jiang Yuan in the coming International Ultrasonic Symposium in Taipei. I hope friends, colleagues, we can go there to memorize Dr. Jiang Yuan and his contribution to this field. With this IVUS imaging, the other challenge what we experienced was the vulnerability. This is one of the artery to show. You see the plaque build up, and this plaque is also very minor, we call it vessel assortments, micro vessels fuse into the plaque and into the vessel wall, right? That kind of vessel assortment structure is a great biomarker of plaque vulnerability. And then at that point, Dr. Jiang Ma led this work in our lab. We're trying to develop a superharmonic imaging technique to identify those, to image those vessel assortment structure and to identify this vulnerable plaque. This is a collaborative work with Professor Paul Dayton, UNC Chapel Hill, and Professor Kirk Sean and Chifa Zhou at the University of Southern California back to about 10 years ago. And this is the first paper Jiang Guo published, and that was the cover of IEEE Ultrasonic journal transactions, right? As you can see, we deal this kind of problem with the dual frequency design. With one frequency, low frequency, we transmit acoustic wave so that we also inject the microbubbles into these blood vessels, right? And that low frequency transmission at here, about 6 megahertz or so, they can exercise this microbubble to trigger the nonlinear response from microbubble so that we can use a high frequency, in this case about 30 megahertz or so, to detect those higher harmonics to form this image. This is still related kind of contrast enhanced ultrasound imaging, but we will do that in the higher resolution. As you can see here, this is our 3 French assembled dual frequency IVUS catheter, and then this is the bottom side here is a B-mode image, in vitro image about 200 micron cellulose microtube, filled with these microbubbles. We were able to image that clearly with this dual frequency IVUS transducer Jiang Guo developed. On this superharmonic IVUS imaging, we also have Dr. Zhuocheng Wang. He's now assistant professor in Tianjin University, and Dr. Sibo Li is now leading a startup in Boston area to develop more advanced ultrasound imaging techniques. We also did more kind of phantom imaging. This is the 200 micron cellulose microtube. We can see clearly, we can see the contrast only superharmonic only image, and also this one is the one we added with the B-mode image, so we can identify those 2 microvessels clearly. This is a chicken embryo in vivo imaging, as you can see with optical images here to show the different microvessels developed right in the chicken eggs after some time to the hatching, right? And then we do the superharmonic IVUS imaging to do the 3D reconstruction. Clearly, we can see some of the major microvessels developed. The reason we use this, one is this is the cheaper than the animal model. The other is actually those microvessels, the dimension-wise very similar to the vasa vasorum in the human's coronary artery, the plaques. So that's for the superharmonic imaging. Next, I will shift to interventional imaging, what recent work we did. Based on that, micro machine 1-3 composite. This is the collaboration with my former student Wei Chan and Dr. Jiang in CTS. They can provide this kind of high frequency 1-3 composite right now. What the Ben led this study. Ben is our current PhD student. Well, we realized in some cases in the biopsy, this tumor biopsy, sometimes you get biopsy needle get into the tumor side, not guarantee you can get the right side to get out the tumor tissue you want. How to improve this biopsy precision? And when we came up with the idea, we integrate that high frequency ultrasound transducer with this biopsy needle, and then at the same time, we can do when we proceed this biopsy needle, they can do the tumor imaging, right? To see whether, we hit the tumor at the right location. So this is the preliminary results we just published this year. Next is about intravascular sonus thrombolysis. This is sonus thrombolysis is a technique to treat blood clots. We know the blood clots, this is increasingly a more significant problem, especially post-COVID-19. Blood clots bothered more people than ever. But here from this clinic website, we know there are 7 factors that promote unwanted blood clots. We don't want it, right? Those 7 factors small, but I zoomed in here, you see immobility. You don't want to sit there still for too long, okay? That's why you take the flight. Some people use that, to prevent the blood clot from forming, right? And then smoking is not a good thing. The inflammation, sometimes if there's any inflammation, treat it, right? Surgeries, injuries, hormone and disbalance and obesity, all those are related with blood clots. And blood clots that develop, sometimes they quietly, okay, until someday severe, symptom happen, especially, if the DVT or deep vein thrombosis develop in the leg area, you probably just feel a little bit kind of odd or sore in the leg. But once part of that blood clot, separated or split from this main DVT and then migrate into the lung area, that was a big thing. We call it pulmonary embolism or Fish-Shuan-Tsai, okay, PE. PE is very deadly. We all know that, right? So to treat this blood clot in early stage is very critical. Currently, the number 1 treatment is still we call thrombolytic treatment. It's just use a heavy dose or high dose of thrombolytic agent, right? To try to dilute, dissolute those blood clot. But the thing is, those thrombolytic agents in principle, that's just blood thinner. If there's any bleeding caused by this or other reason, then it's hard to stop the bleeding. So that's something that's very dangerous. Okay. There are some other ways using the mechanical way. We call the thrombectomy. You can use the diamond-coated, catheter, or use the flow jet, or use aspiration to suck out those blood clot. Those are the movies. Because of the time, I'm not going to play here, but you can know those are Rotarex, Angiojet, or Clot Hunter. Those are the typical thrombectomy, a mechanical way to remove blood clot. Right. In general, those mechanical ways, they have challenge about vessel wall damage, that there are tremendous stress over there. And also there's a challenge about distal embolism, which we do not want to see either, right? And then there's an ultrasonic solution back to probably 10, 20 years ago. It's called Xiaoning system. What that is, they use this ultrasound wave to enhance the drug penetration. You have the thrombolytic agent, put into next to the blood clot, and then using ultrasound wave to enhance the drug, penetration. We know sonoporation, ultrasound can help the drug penetration, right? So that's true. But this has some improvement, but more improvement certainly is needed to reduce the treatment time. When we're talking about the treatment time, the average treatment time of this DVT now is about 15 hours. And some of those could take weeks, months. And one time, there was one patient, the child patient's mom emailed me, those could be years to handle this. This is a very nasty disease. All right. So how to do that? We came up with the idea we call forward-looking intravascular sonal thrombolysis. But our idea is if you have a blood clot here, we want to bring the microbubbles here and then using ultrasound to cause the cavitation to disrupt this blood clot more effectively. Right. So that's really inspired by some of the work we know. The cavitation sometimes, and people think that's not a good thing. They can cause erosion, can even cause erosion in the metal material, right? But in our case, if we use this cavitation to disrupt blood clot more effectively, that will be a big advancement in this field. But the challenge here to come to, we need to build the small ultrasound transducer into this blood vessel. And you say some other people already developed, but that previous one, they just for drug delivery. In this case, we need a higher energy to cause the cavitation. Why we need this cavitation? We know the cavitation, we call it stable cavitation, we have inertial cavitation. The stable cavitation, basically you have a microbubble here, just oscillate, or vibrate, or get expansion, contraction. So that will cause some of the microstreams around the microbubbles, right? And the inertial cavitation will be the microbubble will get collapsed at some point. All this because of you see here, this equation we call Rayleigh-Placid equation, we govern that. If the R is the radius of this microbubble, and you see the pressure difference between the inside of the microbubble and the outside microbubble will determine the radius, right? If you generate the inside the microbubble, that the pressure you cannot control. Usually is fixed. But outside, we can use acoustic waves to cause a negative pressure so that we make this microbubble will expand. At some point, it will cause this collapse. We call this inertial cavitation. So that's the idea. Now we know when to utilize cavitation. But the cavitation, we all know that cavitation really, the low frequency is a favorite for cavitation, normally lower than 1 megahertz, right? And for the blood vessel, intravascular, we need a small aperture. And the small aperture usually, is less than 2 millimeters. It's small. And we all know low frequency, small aperture, they do not get along well. Low frequency usually means large aperture, large size, right? And the large size, is not allowed. You get small size, high frequency, cavitation is not allowed. So that's really, kind of the challenge, because at the same time, we still want to have reasonably high peak negative pressure. If you're familiar with transducer design, you look at the pressure wave, pressure distributed along the actual directions. Really, we want to hit at the near field length. But with this small aperture D, the low frequency F, it's hard for us to get this the near field length with well-developed acoustic waves, right? But that's okay. Even in the near field, you get some of the as non-stable pressure, as long as it can reach a certain amplitude that can cause cavitation, will be fine. So that's why we came up with this idea to do this low frequency a small aperture transducer. There's another challenge. For those of you who do the RF device, the electric impedance matching is very critical. In this case, we have small aperture. Low frequency means I will have really low dielectric constant or electric impedance of this, single layer piezoelectric transducer will be really low. We're talking about kilo ohm. That's not efficient in terms of the RF power transfer. So we came up with a multi-layer design. We know in the capacitance side, people make these multi-layer capacitors, right? This is exactly the same multi-layer piezoelectric ultrasound transducer. Then we can enhance the capacitance of this stack by the square of the number of the layers, right? And that tremendously will help reduce our the electric impedance of this small ultrasound transducer. And the good thing is that's very challenging. It's really small. You get multi-layer. All these, it's use your hand to align and to bond. But the good thing is Dr. Jiang came at that point. He was our star graduate student. He was able to make this beautiful alignment, multi-layer stack. And then as you see the photograph picture of these small transducers. Dr. Kim right now is also a professor in the it's a Kompo National University, right, in Korea. Right, and then it's not a surprise we using the a hydrophone did this acoustic mapping. We see this is a near field acoustic field developed well. It's about a few millimeters. This is good enough because we bring the catheter next to the blood clot, right? So a few millimeter, 1 to 3, 1 to 2 millimeter, that's good enough. So, and the good thing also look at the peak negative pressure, the red dots here. This one, the triangle one, actually, those are peak negative pressure. Indeed, we can get to about 1 megapascal in the first prototype. That's good enough to cause cavitation in terms of mechanical index, right? We know later on, Bois was able to build beautiful, a small aperture multi-layer transducer. He was able to make the peak negative pressure a few megapascal. So that's more than what we need. And then the next thing that we did in about 2017 time, we did the in vitro test. As you see the movie, whenever we turn the ultrasound on, the blood clot will be disrupted very effectively. So that's, the speed-wise, it's more than 10 times the conventional or commercial ultrasonic method. So that's very promising. Mechanism, we came back to detect the cavitation without microbubble infusion. We see the clear natural mode here is about 700 kilohertz, right? But after we have microbubble infused, we did the cavitation. You see there are so many harmonics come out. That's clear indication. Cavitation events significantly enhance that causes this effective smolysis result. So move further, later on found, microbubble helps, but microbubble usually in the circulation will take minutes, a lifetime long. So that's sometimes it's not we want to see. We want to see some treatment, want to see could tens of minutes, could even an hour or so, it'll be more helpful. And then we come up with a nanodroplet idea. The nanodroplet idea is the size-wise can go to 100 to a few hundred nanometer. That's small. And the good thing, they can also, there's a good probability they can penetrate inside those blood clot. So we can have an inside-out kind of cavitation. Now you think about it, you build in this small bubble bomb inside the blood clot and cause the bomb, collapse or bombing. You can imagine that would be an awesome idea, right? And indeed, Leila Goyle, she's now a scientist in the Shockwave Biomedical in the California area, and she did this retracted clot because we first tried this microbubble with ultrasound with the retracted clot. Retracted clot also refers to aged clot. In the clot there for more than 3 days or even weeks, months, right? They're very dense. And that kind of clot is really hard to deal with. Even with the microbubble, with our intravascular thermolysis technique, we still less than 15% reduction rate. So this is not clinically significant yet. And the good thing with this nanodroplet, we use TPA with ultrasound, will bring that up to about 40%. So this is a very impressive. And this is also one of the very first paper we demonstrate this effective retracted clot lysis. And as you can see, we want to enhance cavitation, right? And the cavitation, you need microbubbles. And if you flow the microbubbles inside the blood vessel, the blood flow will take away most of the blood, a microbubble very quickly, right? So how to keep the microbubble next to the blood clot, right? And then my student Bois, he's now a research scientist in the company, same company Sibo is leading right now. Well, Boa came up with the idea we can use magnetic microbubbles. This is also collaborated with a professor in Nanjing as Dr. Yu Gao, and he can make those magnetic microbubbles. And Boa utilized the magnetic microbubbles with the external magnetic field, right? Apply the external magnetic field so that we attract this magnetic microbubble just next to the blood vessel. And then we introduce this acoustic wave using our previous catheter ultrasound, and then you can cause this cavitation more effectively. And even more, because you remember cavitation will cause, the microstreaming, microbubble vibration, the collapse, and then he can add one more layer of this using the rotational magnetic field so that it can, drive those magnetic microbubbles moving around this blood clot that's causing more microstreaming. So this is really a great idea. That's what Boa is also very good artist. Okay, all those the drawing all from him, so he got the credit. And the one thing I want to point out from this blood clot you see here, with the retracted clot, with this magnetic microbubble and nanodroplet combined, he was able to bring the thrombolysis rate above 50%. This is a major a breakthrough in this field in recent years. And even more, we want to cause this, chaotic microbubble movement and the vortex, right? So that is inspired by the vortex idea. When I talked to this technique with Professor Chen Zhi Lao, he was in Georgia Tech at that point. He did a lot of the acoustic vortex work. When I talked to him, he goes, "Hey, Xiaoning, we can bring this vortex into your technique." And then indeed, after a few meetings with them, we built this the first prototype. This is the easiest way to generate vortex and also the cheapest way. Again, Boa, Howok, and Huayu, those three work together to build this small, piezo stack here. Each one is about less than 1 millimeter or so, and the total is about 1.8 millimeter, about 1.8 millimeter. Okay, 4 piezo plug over there. All these piezo pillars, they are driven with one electronic channel. Okay, so that's why I say this is easy and cheap. And then from simulation, we should be able to see the acoustic vortex. Well, the acoustic vortex is nothing but acoustic wave with helical wavefront, right? And then this sketch cartoon can show you, we want to build that into the catheter with the vortex, wave get into the clot. If you see this, it's more like, hey, Xiaoning, this is you're using the drill, mechanical drilling through the clot. Yes, that's a mechanical drilling, similar, but we use acoustic drilling. Okay, the device is not in direct contact with the blood clot. We published this last year in Research. Again, thanks for the research. Really provided a great platform for this. And this is to show the device to show how we cause using the particle to demo the vortex formed with this vortex ultrasound transducer. That's really, when we first saw this, we're really excited. And Boa demonstrated this. Later on, we built a really long, phantom 3D printed venous. This is mimic the Sinus venous system, okay, in the brain. And as you can see here, it's really long, multi-centimeter long. We use this, catheter is about here. We're going through we call this to, generate a channel through this so the blood flow can go through. So that was very interesting there. So we talk about the in vitro study, not just the efficacy, right? In the medical device, we know efficacy and safety, they're equally important. In terms of the safety, we look at, the concerns about thrombolysis would be, we don't want to see the tissue heating because of the ultrasound device. We don't want to see the large clot particles that will migrate to other places to block the blood vessel over there. We also don't want to see the endothelial layer damage in the blood vessel wall, right? The hemolysis, that's another layer of concern here. So that's kind of the the safety study we conducted. Again, Leila conducted this The first is the temperature rise, as you can see here, with all different kind of the treatment condition, with ultrasound alone, with TPA. TPA is a thrombolytic agent, okay, microbubble, nanodroplet, or combine of them. As you can see here, we don't see significant temperature rise. The highest one is lower than 0.8 Celsius degree. So that presents no concern at all in this study. We know this because the reason is that we use a really low duty cycle, and we use less than 7% duty cycle. So usually that's not the major concern of ultrasound induced heating issue. Particle size, similarly, Lila did what she did, to look at with different conditions, look at, what kind of particles. You see the particle, the different color means the particle size. The orange one is particle size about 50 to 100 micron, and you get the largest one is about 300 micron. It's a dark blue at the end. We didn't see any of those. So that's, again, there's no blood clot, debris greater than 1 millimeter is not concerned here. And next, we look at the endothelial layer damage. Consider using the histology, look at control TPA on a different treatment, right? As you can see here, all their histology showing similar images. There's no typical cell damage in those treatments. So again, that's a really good sign too. With those a safety study, that's mostly ex vivo. And then we get to the next in vivo test. I'm really glad to see a few days ago, our first in vivo test was accepted by engineering journal. So this, as you can see here, what we did, this is the collaborative work with Professor Zheng Xu Zheng 老师 in University of Michigan. She's a pioneer in this field. She developed this DVT animal model, pig model over there. What we did is, in the femoral vein here in the leg area, right, we generate this the blood clot over there with centimeter long over there, and then we introduce our catheter inside, and then to do the thrombolysis. And as with one test here, we see this angiography, right, fluorescence microscopy, as you can see here. As in this case, before the treatment, we're able to see the blood clot form. Supposedly, this is the vein. If you follow my marker here, laser pointer here, you should have blood flow going that way with a contrast. But because of the blood clot formed here, they blocked here. But after treatment, catheter treatment, we're able to bring that, much further within 10 to 15 minutes. So that's really, as you can see, the length of that progressing is here. So this is, really high speed in this case. And the bottom here, we show the Doppler ultrasound imaging. And the left side before treatment here, we see the artery, you can still go through because we generate the blood clot inside these veins, right? And vein was blocked because of the blood clot there. But after the treatment, you see the blood flow regenerated, reinstalled in both in the vein and also the artery. Of course, you have the blood flow there too. So this is it's very successful first in vivo test, and they show some movie here to show the Doppler ultrasound imaging to see, with vein only and with both vein and with artery only in the left, and artery vein flow can be clearly shown. So that's very successful. And, during those in vivo tests, we experienced some challenges because in the lab tests, you can easily see because most of the tubes are transparent, you see where the blood clot is, move the catheter, right? But in the vivo test, we couldn't see that. With the angiography, X-ray, or ultrasound image, you can see something, but we know in future human treatment, that's going to be very challenging. So we have an idea, then we want to build in the imaging capability into this catheter. So this is the first one where you demonstrated we have a high frequency, about 20 megahertz transducer integrated into the catheter together with low frequency thrombolysis transducer to the treatment. As you can see here, after the treatment, we can see the boundary can keep going so that we can trace how long the treatment is and where the blood clot is. So this is the very first demonstration. And this is the one, it's a collaborative work with Professor Jing Yao in Duke University. Yu Qi is Dr. Yao's PhD student. She worked with Huayu on this project. And what we introduce here with the photoacoustic imaging, what with Jing has this optic fiber, laser fiber integrated with our transducer. We shoot the light here and cause a photoacoustic signal, and then we use external ultrasound to pick up that signal so that we know where the blood clot is. So this was very successful too. As you can see, with Jing was able to put down about 10 centimeter, is that right? 10 centimeter, right? Yeah, 10 centimeter thick chicken breast on top of the blood clot in the tube, right? If you do the ultrasound imaging, you see the chicken breast tissue over there, you see the tube over there, but blood clot is hard to see where it is because the contrast there is not good. But with photoacoustic imaging, combined, clearly you see where the blood clot is. So that's very promising results. Jing and I, we were trying to secure more resources to advance this research. Now let's look at the drug delivery side. This is the early work. Even though we published more than 10 years ago, I saw still this is represent one of the unique precision biomedical ultrasound research. At that point, this is a collaborative work with Professor Jiang in Penn State. What we did is we have this small micro, as you see, 25 micron by 25 micron, those ultrasound transducer, right? Integrated a chip, biochip. And top of that, you have this, melanoma cell cultured in this medium. And inside the medium, we have some quantum dots over there. So if we turn on the ultrasound, the quantum dots will get into the melanoma cell in seconds, right? Because of the sonorization. If you do not put this ultrasound, so other cells without ultrasound sonication, it will take about 24 hours to get some of uptake, similar uptake. So that's, if you do drug delivery, we believe this cellular level drug delivery, using the ultrasound, a localized ultrasound, is a great approach to enhance its drug screening. And this is a work also use this work with collaborated with Professor Zheng Guzhen Laoshi when he now he's in Jiang University. When he was at NC State, we're really happy. At that time we worked together, demonstrated using the ultrasound patch, which Dr. Gu's student Jin Di, she embedded this insulin inside the nano network, and then we use ultrasound to trigger that release. That was very successful, at least, with this animal test showing here. This is to show the blood glucose level, right? If without, any, insulin treatment, they will maintain the high level. But whenever you have this treatment, the glucose level will drop, so that we can do that multiple days. We wanted to advance this, but unfortunately, Professor Gu left NC State, and they, so we couldn't continue. This is something I'm still interested in. And more recently, my student Meng Yue is doing we call it intratumor. And for tumor treatment, you thought that you bring the drug into the inside the tumor. You think the mission accomplished. No, that's not. I recently talked to a surgeon, Dr. Kim Lyerly in Duke University. Well, he told me whenever you inject those drugs inside tumor, that tumor is more like the rubber. The liquid flowing back sometimes get to the surgeon's face. Okay, that inside we call it anesthesia pressure is pretty high. The drug is very hard to be absorbed. So we came up with the idea trying to use this ultrasound needle to enhance that. So this is the preliminary results. Meng Yue is still summarizing more results. Hope to see the journal publication soon. This is the cartoon shown in our review paper published last year, led by Dr. Asada in Duke. Now he's in Tokyo. So to see with that ultrasound needle inside, we can possibly make many things, good things happen. In particular, will be immunotherapy could benefit from this method. Again, this is just the idea yet. Hopefully, we'll see more results in the Now, we have a few more minutes. I will move quickly to the wearable ultrasound, which I believe also belong to the precision biomedical ultrasound. This is the work the first we demonstrate the flexible ultrasound transducer. As you remember, most of ultrasound transducer, we use rigid piezo material, either ceramic or single crystals, right? Single phase or composite, but composite is rigid. You can argue, say, oh, composite, I can use this flexible, polymer or resin to fill the curve so that it can make it relatively flexible. That's okay. But the electrode was the issue. We couldn't fix it until I discussed with my colleague, Professor Jiang in my department, and we will find out his silver wire network, right, with PDMS, that composite is very stretchable and bendable and flexible. We utilize thin layer of that as an electrode, and then we clearly, as you see here, we can bend this piezo composite whatever the way we want. So this is a very interesting. This first demonstrated by Jiang Kim is now professor in Korea, and very successfully. And then Professor Peng Changlas is now with the Shanghai Tech as a professor over there, and he demonstrated for the first time using this flexible ultrasound transducer to do the blood pressure monitoring, continuous monitoring here. And what the idea is, we use the flexible ultrasound transducer to detect or to monitor the vessel wall artery, vulnar artery diameter. And with that diameter here, we can correspond that to the blood pressure. That match with the clinical measurement very well. So that's where now we got another fund recently, seed funds, to continue this to see if we can go further. This work is about wearable ultrasound using those flexible ultrasound transducer arrays to monitor the muscle continuously. This is led by Dr. Xiaoning Xue in our lab, collaborating with Professor Nitin Sharma in the BME department. And the idea here is with assistive robot, and the people have a hard time to walk, right? You have that robot to help provide help, but the muscle, we need to make sure sometimes muscle can get fatigued, right? You do the functional electric stimulation to stimulate the muscle, but if muscle in fatigue state, you don't want to continue that. You should enhance the assistive robot torque or force. So how do you know the muscle is in fatigue or not fatigue state? And Xiaoning, came up with this idea together with Dr. Sharma. We use this ultrasound transducer to look at the displacement or elasticity, right, at a different angle, different muscle. Whenever the muscle in the fatigue, we know the elasticity is not that anymore, so that we can make the control so that we use the assistive robot more brilliantly. Okay. The next wearable ultrasound is collaborating with Professor Wen Feng. I believe, Alice, you met Dr. Feng when he was here in Duke University as the chief stroke division chief. We came up with the idea, we want to help the stroke patient in some ways to do using ultrasound to do neural stimulation, okay? And how to get through with this ultrasound, get through this human skull and hit the certain neural region. That's a challenge. The first step we did with the human skull, we did the in vitro water tank test. That has been very successful to help us to design this wearable ultrasound to do the future to this neural stimulation for a stroke patient rehab. All right, so this is a quick summary here. As you can see here, we reported our recent progress on this precision biomedical ultrasound. In particular, we found that interventional ultrasound transducers can be successful in precision biomedical ultrasound imaging and therapy and drug delivery, right? And you can also see there are tremendous future work we can do. And certainly with the new AI development, we can make those interventional ultrasound imaging therapy or imaging guided therapy or drug delivery or implanted ultrasound be more intelligent. When I'm saying be more intelligent, either you can detect the target more precisely, or you can deliver the drug or doing the therapy, hit the target more accurately. Okay? And wearable ultrasound certainly is another important precision biomedical ultrasound technology, because we believe continuous monitoring or in-demand monitoring is very important. It's not always you go to the hospital and then using that. We know that's important. Hospital, you cannot replace hospital, but in home or continuous monitoring for some risky population, that certainly is very important to enhance human health over there. And the last, but probably is most important, we're all doing the biomedical ultrasound device research. We're happy with good publications, but we always want to keep in mind that we want to translate this kind of a new technology into clinical practice, because that's the way to help human being at the end, right? With that, I would like to thank my collaborators, former students, postdocs, funding support. There are sort of conflict of interest about sonovascular license, those intravascular sonolysis patents, and they are really in a very good progress toward the clinical trial soon. With that, I'd like to thank you. Hope you found this the work is interesting. If you have any further question, please email me or ask after this talk. And also, I'm looking for hardworking and students to join us, and postdocs as well. Thank you.
Okay, great. What a spectacular talk. So really learn a lot. So before we go to the question part, let me first introduce our panelists. Let me share the slides. And okay, Xiaoning, really congratulations. Your talk was so interesting. We track a lot of people here online. Actually, let me first introduce our panelists. We have a Jiang Ma, was from Beihang University. Actually, Jiang was, got PhD with Professor Jiang, and then, did his own job here, very, very good. Recently, he got a big funding. I think he just share us, some good news that time. So, Jiang, welcome. We have another good friend was Kim, was from Inha University, Korea. He also, got a PhD in Professor Jiang's group, and then spent few years applied material, and then back to Korea for his own academic career. So welcome. Yeah. Oh, Howard. Yeah, sorry. Yeah, Howard. So I hope I is right. Okay. We have Meng Di. Yeah, Meng Di. Actually, as assistant professor at Peking University in the future in the future school. So yeah, the school name is Future School. Okay, it's a major for biomedical, research. So Meng Di recently got some good results. Also, in this biomedical implantable, sensors, animatory. So I hope you have a good questions. Yeah, we have our challenger here is Wan Ji. So was a PhD student at Peking University. Wan Ji was doing a lot of work about magnetic, wireless, is transmissions and testings. So we have a G here for our challenger. So as normally we got everyone on the stage. And we start the questions from our challenger. Wan Ji, are you ready?
Yes, Professor Zhang.
Okay, please.
Yeah, thank you, Professor Zhang, for your wonderful talk. And I have learned a lot about ultrasonic. And I have I have two problems. The first problem is about the magnetic particles, because I am now doing some work by implanting magnetic materials into the body. So I'm curious about the particles. And the problem is what's the size of the particle and how to absorb these particles absorb these magnetic particles onto the surface of the bubble. And also I'm also curious about the biocompatibility of the magnetic materials.
All right.
Yeah, this is the first question. Yeah.
Okay, thank you, Ji. Yeah, indeed. That has been a concern. Whenever nanoparticles, actually, people in general are very, very concerned. FDA is very cautious to approve those anything involved in nanoparticles. Okay.
Yeah.
The magnetic nanoparticles, no exception. It's a concern for sure. But the good thing is this magnetic particle is they use in I believe it's the ferrite oxide. It's with size is in several hundred nanometers, and we are not the one how to attach them to the microbubbles. We cannot do it. But Dr. Yu Gao in Nanjing, I forgot which university, Nanjing Youdian Daxue, probably, yeah. There's some university like that, right? He's really good at that. I can dig out his contact if you want to reach him. And get back to the safety concern. The good thing with ferrite, that nanoparticle actually in the blood that can be absorbed with certain dose, and that turned out it's not a concern. They can absorb pretty well through the circulation system with certain dose. But again, you cannot. Some of us we actually there's one supplement, right? Is you eat some of those. If you were, but again, there's a dose control for sure. But with this microbubble, magnetic microbubble case, the dose we're using, I believe we haven't done any safety tests with animal, with human, but from our original calculation, that should be within the safe dose range.
Yeah, thank you very much. And the second question is about the wearable ultrasound devices. And I have a question about will the stress during the bending process affect the piezoelectrical materials and the imaging effect? And also, I think by wearing this device on the skin, there may be some interface problems because the device, maybe we need a glue to attach the device to the skin so that there will not be air in the interface. So I wonder, will the interface be a problem for the imaging application?
Yeah, this is the brilliant question and very great. So the first part about the bending or stretching will affect our piezo property or imaging. Well, that is indeed piezo part, because we still use the piezo composite. We have a solid piezo pillars of place embedded in a flexible matrix, right? And piezo material itself with that stress should not be affected, because that stress is very minor compared, because they are still solid, right? But overall, acoustic wave will be different because you're bended. The acoustic wave go out. The aperture is not flat anymore. You have a deformed aperture. That regard will affect your imaging. In terms of because your aperture changed, your field of view will be different, right? And then your imaging, field of view will be different. So that's for sure. So that's why, in our case, for our blood pressure monitoring, we pick the low-hanging fruit. The easiest we use single element, as long as we align with that Worcester artery, we're okay. But if you do a large array imaging, the beam forming will be very challenging. It's flexible. So you will need to know the position of each element so that you can construct the image, right? I know Professor Junjie Yao and Xiaoning Ni in Duke University, we and my group were collaborating on something like this, and also we work with the UIUC Professor Pengfei Song. There are some interesting things in there. This area is still ongoing. I know there's some published work from Dr. Shen Xu's lab and Dr. Xianho Zhao's lab. They show some of those results too. So that's to hopefully answer the first part of this question. The second part about this, pardon me?
The interface between the device and the
that's always important, because we're looking at continuous monitoring, right? So for us, I give a baby as an example. The baby sometimes don't want to wear anything, right? So because they wear something, is to them it's a restriction. You don't feel free enough. So in these wearables, certainly we know some risky population, you have to sacrifice some part, right? But this part, the interface, is very important, because one importance is coming from the coupling, acoustic coupling. You want to make
Yeah.
sure your acoustic wave or acoustic echo come in and out through that interface without much problem. We usually in ultrasound, we use ultrasound gel. That's kind of liquid, right? But
Yeah,
also,
yeah.
that's liquid gel. You can do that, but that's not good for wearable. We know that. And that's why in the recent publications in MIT group and UC San people intend to use either adhesive interface.
Oh.
It's called bioadhesive, or we're also interested in adhesive or in the dry coupling. And some
Yeah.
ultrasound coupling, they can be dry and have a good adhesion with the skin and the transducer, but it's not adhesive. It's not liquefied, right? So that's good. But still, there's more study need to be done in terms of interface, whether or not it will affect the skin. We all know if the skin, you have that kind of good acoustic coupling, sometimes means that skin might have some problem if you wear the too long, right? So there's still something ongoing there. I don't think that's the question can be fully answered yet. We know the concerns, we know the direction to go, but that problem is still open challenge.
Yeah.
Thank
Thank
you.
you very much. Thank you very much.
Okay, yeah, great answers. Okay, who is next? Yeah, Jiang, are you there?
Yeah, sure. Okay, thank you, Dr. Jiang. Very great talk. And thank you also for introducing my work here. I have two questions. The first is a technical question. It's about the magnetic nanoparticles. You used a magnet to attract the particles inside the blood clot and got remarkably high dissolving rates. So I see it should be in ex vivo, right? What would happen if you want to do it in vivo, because the vessel is very complex inside the body? So how do you comment this?
Yeah, Jiang, that it's hard. Ex vivo, kids love the first stuff, in vivo, ex vivo in lab, right? It's because you can see, they can control really well. But that's still important in terms of demonstrating the concept. But at the end, as I said, we need to translate, because the in vivo can translate. This is going to be a challenge over there. Again, down the road, we still want to using that imaging catheter to provide us the position, and then that will coordinate with external magnetic field. That's our current idea, but again, we haven't done the in vivo test with the magnetic microbubble yet. So we need more resource. I'm really jealous about the resource you guys have. Yeah, but yeah, that's a great question. It's ongoing and the future work. We definitely want that to be done. Yeah.
Okay, thank you. The other question is not the technical. So we know that you worked for a while in industrial, and also you have several translations. So would you help us, give us more suggestions on the translation, like how to make our ideas to the real products?
Oh, Jiang, that question should be answered by Professor Jiang. Well, since I worked in industry for 9 years. The first industry work right after Penn State, I went to Long Island, New York City. That's the standard MEMS, and that was 2001. I remember that day when President Bush Jr. swore in office. I was driving my Oldsmobile, really old car, on the way from Pennsylvania to Long Island. I listened to his swearing, all the stuff. Get there, it was a good standard MEMS. At that point, was the largest MEMS company in the world at that point. They have 3 fabs, 4-inch, 6-inch, 8-inch, one in Long Island, which I worked in, one in Milpitas in California, one in Germany. But unfortunately, that year, you probably don't know, Professor Jiang, for most of us, we know that year, first, there was a telecom bubble, right? So, and then 9/11 happened. But my family, at that point, my son was not born. My daughter, my wife, they still stayed in the Pennsylvania area State College. And then, it's really not that few days. And of course, a couple of months after that, it's really very tough. So then I went back to State College area. Unfortunately, the company, I declined to join the Long Island company. The okay for me to come back, to join them again. So I joined them in 2001 there, and then we worked in that company for some years. I know with a small company, that's also a small company, a spin off from Penn State, and they mostly do this piezoelectric material production. They're very good at very famous now. It's called TRS. They are for the single crystal growth. And I know it's not easy to get anything, right? But when I get to the NC with that industry experience, so for my mindset is slightly different from most freshly graduate, professors. Every new thing, when you work here, you know that anything new come out, we can't wait to file invention disclosure or file patent before we publish the paper, right? And then that's the thing. And then when the paper published, our patent also pending. So it's not conflict with each other. It's just a way you can secure the IP, and then if you have people interested, they can help you to translate that, right? The translation is not easy. You have a lot of tips. I think it's beyond my. I myself is not a successful entrepreneur. Put that way. I did work with a few folks, friends and the colleagues on the different startups, but overall, I will leave that to Professor Jiang, and also go to Davos, so you will know more.
Yes, actually, you got me recall that, very tough time at 2001 or, 2002. Actually, MEMS before this was a huge, blossom. So many MEMS conference, but suddenly, almost most of them were shut down. Yeah, especially many, RF, MEMS and optical, and for the mirrors, many was shut down. So that's a big change. Yeah, I don't know you exactly in the company that time. That's really shock.
I saw
but you are
the
exactly.
rising. Yeah, I saw the rising, thing on the way. I lived in the Stony Brook. I drive to the west. I saw the huge smoke in the city area that morning. Yeah, that's crazy.
Okay.
Well,
Yeah.
back to you. Sorry.
Yeah. So great. Yeah. So actually, you're exactly right. It's not, easy to make, any commercialization, for the translations. Yeah. So we really need long time. So we will discuss this and Davos. You're right. Yeah. Please go there. We have many news to share. Yeah. So Howard. Yeah, please.
Thank you, Jinko.
Oh, right. Thank you, Dr. Jiang, for your great talk. And I appreciate for mentioning my work in the presentation too.
Sure.
So I have two questions. So for the case, we ultrasound engineers have struggled to achieve high accuracy, high power ultrasound energy in a physical transducer. So, but yeah, yet most technologies are just related with improvements in piezoelectric material and focusing lens, and so do you think what will be the next generation of the technologies in the ultrasound therapeutic transducer beyond the current technology?
Oh, this is huge question here. Well, I'll try. I would say, material, certainly we all know material means a lot, right? It starts from there.
Yeah.
Because you get energy, electromechanical energy coupling, without excellent material, that we cannot go anywhere. But I do believe the design part have a lot more work to do, and fabrication, manufacturing side too. Let's first look at the design side, and the design actually theory has been in place probably for multiple decades, probably 4 or 5 decades, right? And there are not many new concepts coming out, but until recently, we believe there are some of this multi-layer design, and also more recently we talked to some people with acoustic meta-structure design. That could be something help us to define the waveform for particular application. I'm not saying that's good for every application. If you for histotripsy, that's different for neurostimulation, right? So it's just a different. But I do believe acoustic metastructure should play a big role over there. The other thing I think in terms of the the manufacturing side, how you make the different structures or transducer structures in a more efficient way to form a for I give example, if you want to make large 2D array, piezoelectric 2D array, that's still not easy, right? And how if you cannot make that available, and then people doing the imaging, doing the translation or clinical translation, it will not benefit from the new imaging method and the stuff like that. So I do believe those large 2D array or even 3D array or flexible arrays, those are still manufacturing still a challenge to the researchers. I know the big, usually say big three, but big more now. Those big companies, they have that facility to make some of those, but they usually do not open the platform to researchers to doing the imaging direct algorithm development and then more application developments, right? So that's manufacturing side I do see, and then in terms of the getting to the wearable side, I believe the interface and the wearable is not just the transducer itself wearable. You got to make sure the power supply, the communication, right? It's all wearable. Really, it's just a watch is typical, or you get something small, light, and that can last a long time, right? And yet still environmental friendly. There are many of those things could come. And the other direction going to the implantable. We see more ultrasound for power transfer. You can say using EM wave to do that, but ultrasound has some uniqueness in deep tissue organ without any interference with other device, right? So that you either have the ultrasound device embedded or using ultrasound device to transfer the power to power the embedded device or implanted device. That's something I believe is also very important. It's ongoing development. So yeah, at the end, that's add with the new intelligence added on in design, in the transducer device design, in the imaging development, in the application. There should be a lot of more opportunities out there. Yeah. So thank you, Howard.
Yeah, thank you. And I have one another question. So as you mentioned, as for the meta acoustic or meta structure, I believe there has been active researches, many researches regarding meta acoustics. And do you think what will be the role of meta lens or meta structure in the future, especially in therapeutic ultrasound? I think there exists plenty of technology potential in meta acoustics, particularly in, as you mentioned, in neurostimulation. How can the meta structure work in neurostimulation, do you think?
Yeah, that would we know the existing one more in as you said, simple lens for getting to the hundreds of kilohertz. Most of the relatively low frequency, lower than medical ultrasound, but there are some can get to with a simple structure can get to as a lens or something. We have done that, and other people have done that, right? And it really going to higher frequency or tuned for different applications. That could will take some time. And for example, for the stimulation, you would make sure you need to count through the skull. You need to count some of the wavefront errors, right? And we know Dr. Yun Jin and Dr. Chen Zhishi, there are a few, and Dr. Steve Comer in Duke, they have done some work in this field, and for some other in the imaging side, I know I heard some ongoing research over there. People want to do in the therapy too, tissue ablation too, to do the multi imaging, concurrent imaging to improve the imaging frame rate. There are it's just It's not an easy task to fabricate. What I heard from them constantly is the manufacturing challenge more than the design side. In design, those metal acoustic folks, they can design things beautifully in the high frequency, low frequency. But getting to the high frequency side, the manufacturing I heard that's been very challenging.
Thank you.
Okay, good. So Mengdi.
Yeah, thank you, Professor Jiang, for the wonderful talk. So first, I have a technical question, on the intravascular ultrasound. So because the catheter is very long and very thin, so my question is how to connect the wires on the ultrasound transducer. Sometimes you have multiple ultrasound transducers inside a very thin catheter. So how to connect those wires?
Yeah, those wires are very small. Jiang can tell you, it's really when we think about those intravascular ultrasound, mostly the 3 French, 1 millimeter up to 1.3 millimeter around that range. And wires, in some cases, if the one element, the challenging part is because you need to rotate, right? So in that part, they have to have a transformer inside to switch around at high speed. So that's for the rotational ones. If not, so for rotational one, the good thing you only have is one coax cable, right? So that's very small. Usually, 200 micron in that range, right? Really small, sub-millimeter. But in that, I know for the 64 element arrays, they're not going to get a 64 element those cables out. There's no way to build it into that. What they did, they used some of the ASIC circuit, have the multiplex. They get group them, like either I believe it's 8 as a group channel. So the total they only need 6 wires or something come out, a few wires come out, so that they can
I see.
do that wiring. That's certainly a challenge. In some other cases, one have a few hundred channels or elements, right? How to do that? Again, I think a multiplexer is one of the, you need to make those small chips next to the transducer. That's usually the solution.
I see. So additional question to this is the ASIC chip commercially available, or you collaborate with some other groups to design the ASIC for your device?
Commercially, there are some commercial available. Usually, it depends. Usually very expensive. I know there are a few companies in US that can do. I'm not sure in China. There might be some companies can make it, but university labs, I know Professor Chifa Zhou's lab in University of Southern California, they can do something. There are a few other university labs can do something similar like that too. I'm sure Peking University, you can do it. You have all the facilities there, you can do it. But commercially, we don't know yet, but I know I saw some of the quote early few years ago. It's pretty expensive. Usually, with one design, depending on the channels, right? Usually, at that point, I was looking at the high number of the channels. I'm looking at hundreds of thousand US dollars. So it's pretty expensive to most of the research labs.
Yeah, I see. And my second question is on the wearable ultrasound device to measure blood pressure. So you use the wearable ultrasound device to measure the diameter of the blood vessel and correlate it with the blood pressure. So I'm wondering if the correlation is also depend on the thickness and the modulus of the wall of the blood vessel. And because if you use ultrasound, you can also use the Doppler effect to measure the blood flow and correlate the blood flow with blood pressure. So can you compare these two approaches?
Yeah, absolutely. This is a great observation, Mandi. With our method, we have limitation, but it's really good for us. Always, if you have a limited resource, you want to do things in the quick way and also cheap. Don't have make that quick and cheap, right? In this single element, you measure the diameter. That could be very accurate with that frequency. But with Doppler, then you will need to align the angle. In most cases, you probably need more than one transducer element to do that, right? So that could cause a little bit more complexity, but it's doable. I know people are doing that as maybe if we do the down the road, we have a challenge, we probably will come to that, we'll evaluate that concept as well down the road. But to me, if we can do the single element in the wearable and, have a good correlation, there's many variations, you're right. As you said, the vessel wall and those things, we can do the calibration, because when you wear anything, you can do the calibration at the beginning, right? To find out that the correlation factor and then use that, that's good. But the challenge will be if you do the continuous monitoring, your condition change. Sometimes you stand, sometimes you sit, sometimes you're running, right? Sometimes you lay down, right? How do you monitor those continuously? Those will be the challenge. I'm sure the diameter will be different, right? In that case, we believe AI or intelligence will play a role over there. As long as you collect enough amount of data, you have that correlation, you should be able to solve that problem. Again, we haven't done that, but that's just my my guess. That could be the solution. All right. Is that something answered your question?
Yes. I think non-invasively monitor the blood pressure accurately is very challenging, and many
Very
people are
challenging.
trying to do that, and physicians are also very interested in it. If we can eventually monitor the blood pressure non-invasively in a very accurate manner, then it will be it will be a great invention, I think.
I agree. I share the view, with you. Yeah, that's certainly is challenging, but worth of us to put some energy there. Thank you.
Thank you for your talk and answer.
Okay, super. Yeah, super exciting, discussions. I think many can like brainstorming here, get some new ideas. So proud of that. Actually, time is approaching. Yeah, I'm going to close this panel discussion, and I'm so proud to tell you that Xiaoning, today we have the most people on WeChat. So we have over 6,000 people watching the WeChat. Yeah,
Wow, that's
the
my
broadcast.
record
So
forever.
yeah,
So
this
thank
is
you.
really, really great. And normally, we have 2,000 or something, but this time we really have 6,000 there. Yeah.
Thank you.
So
Thank you.
nice, to see so many people working on this lively. Yes, you've done wonderful job. So it's my pleasure to deliver this certification to you. Normally we say that if you didn't answer question, properly, we will not deliver this. Yeah. So
Thank you.
really, really, proud of you and, such a wonderful talk and very, very great, question answers and also inspiring, the ideas to the young generation. Thank you, Xiaoning. I hope next time I met you, I give this paper to you. Okay.
Thank
Now
you.
I
I look
deliver
forward
the
to that,
CE
Alice.
certification.
Yeah.
And so welcome to Davos. As I say that, we have a lot of things, to share and to celebrate. It will be the first time for the iCANX family to go together. The beautiful place and the beautiful talks, the beautiful people. So please go there. So it's time to consider of this, okay? And in the following months, we're going to have a wonderful speech. Yeah, so we will have a Jiang from Stanford University. We have a Xiaoyu was from Berkeley. We have Xinge was from CTU. It just published, on the Nature, for his wonderful achievement. And we have Lu Yang will talk about the computer science. So this we're going to have in next month. So we hope everyone follow our iCANX. For next week, we're going to have a big panel and a big talk. Also, it will be about interface for the light interface and the designs. Please follow this wonderful talks on iCANX and welcome everyone, to focus on this. Thank you very much. Yeah, Xiaoning, so
Thank you.
nice, beautiful.
Thank you.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics. Innovation, Science, Technology, Investment, Management, Entrepreneurship, short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
祝你生日快乐！该吹蜡烛了，来，我帮你。啊！祝你生日快乐！生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，没新意。
那个我的也是啊。
哇塞，这个不是太阳诱电的多层陶瓷电容器吗？小型、大容量，从原材料开始研发，性能和质量都有保证。我最想要的就是这个了，太阳诱电的多层陶瓷电容器。
你没事吧？
机长，还是你最了解我，有了它让我变得更好。我们是彼此需要的关系。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第1次 iCANX 会组织大家一起在瑞士的达沃斯。